The name of my talk is Going Larger Than Memory and Parallel with Graphs. My name is Blake Griffith, and this work is sponsored by Continuum Analytics. And problem a lot of people have that. So sometimes you have data like Richard. So I have around 8 gigabytes of memory on my computer total, and other stuff's being used. Let's say I wanted to do something to this data, like find the standard deviation of it. Bad things are probably going to happen when I do that. So first of all, one CPU core is getting used immediately, not all of them at once, and then some more jump in. Also used all of my memory and starting this, and I might get a memory error soon or something worse. So let's kill that. Walk. Now it's dead, and we're safe. So I'm going to do the same thing I just did with something else. So I imported a different package called dask.array, and this is going to look a lot like what I did in NumPy, but I'm going to add a keyword argument called chunks, and give it some magic number that's 1,000,000, 10 to the 6th, and do standard deviation of it. And I'm going to add another suffix, which is, and run that in. So let's see what happens now. Using all of the cores at once, and my memory changed negligibly, and the cores stopped doing stuff, so we're probably done. And that's the standard deviation of range. Thanks. So, yeah. So that got a little bit of attention. So anyway, back to the talk. So I'm going to talk about the tool that I use to do that, which is called dask. And here is I put a GIF in my slideshow, which was kind of controversial, but it shows you that you don't have to change it to do you what I did with dask.array from NumPy. So dask consists of 3 parts. There are collections, graphs, and schedulers. The collections present an API for making graphs. The one that I just used called dask.array looks a lot like NumPy. And so it creates a graph, and then we take that graph and execute it with things called schedulers. And we have several different schedulers for running the graph in a threaded environment or multiprocessing environment, or a distributed environment, or just synchronously, which is useful for debugging things. So there have been a few talks about graphs, but I'm going to pretend like, well, I'm going to explain what graphs are. So they're not like this. It's not a graph. We use directed acyclic graphs, and that's the mathiest word we're going to use. I'll explain what we mean by directed and acyclic. We have a graph that is directed and acyclic. So this is a graph. It's nodes that are connected by edges. This is a directed graph, so the edges have direction, so the nodes are connected in directions. And an acyclic graph is a graph that doesn't, you start from like a base node and follow the edges. It doesn't connect back to that base. So this is what our data structure looks. This is what a dask uses to represent a graph. It is just a Python dictionary that's keyed with strings and valued with things that are either values or something that dask understands as tasks, which are tuples. That first element is a callable. So does anyone So in get dask graph, we are getting the value of x from our graph and computing it. So we got x here, it would be 1. And if we pass the dask graph and asked it to get the w, so it would recognize this as a task, and then it would fill in x from it would fill in x from 1 and y from y 2, and then it would go get z, and z would resolve x and y and compute the addition and fill this in here, so the sum would be 6. This is an image of a graph that's generated by dask.array. So here we created an array of 30 elements and broke it into 3 chunks of 10. So if you look at this graph, you could see 3 calls to a range. The circles represent function calls, and the squares represent data. So you can imagine looking at this how a blocked algorithm of computing a sum in how computing a sum in a block algorithm works. So you could look at the first branch. You have this might be a range 0 to 9. You compute the sum of just that block, and you hang on to a scalar, and then you do that for each branch, and then combine those scalars to get your result up top. And if looking at this, you can kind of imagine how if you have a graph, you could traverse it and execute it in a parallel way. So if you are just executing along this leftmost branch, you don't necessarily care what's going on at the other branches until you get to the sum up top. And you can execute those 2 branches in parallel without having to share data between them, at least until you get to the top. You can also imagine if your entire array doesn't fit in memory, like if all of these 3 A range chunks don't fit in memory, you don't have to have them all in memory at the same time. You can call this first branch and then compute the scalar, and you can then discard the previous array and then traverse up to the next branch until you just have 3 scalars, and you only ever had 1/3 of the entire array in memory at a time, and then combine. So now I'm going to do another fun part where I'm going to make an array kind of like that and do some more visualizations. It's going to be a 10 by 10 array of ones, and it's going to be broken up into chunks of 5 by 5 arrays. So it's going to be 4 chunks of 5 by 5 arrays. And then I have this array, and I'm going to call visualize on it. And so this will write an image to a PDF file on my computer, which I'll show you. Move that over here. Resize this. I can't resize this. Anyway, yeah, moving right along. We see that we have 4 calls to 1s, so we have 4 chunks of an array right here. So we can do more fun stuff with we can visualize more fun things like a plus a. Don't get tab completion because it's wrapped like that. So if we do this, we can see that we're adding 2 different arrays. Then we can compute the sum of these, like we did in the other thing, to get a graph like this. Or we can do crazier stuff, like take the dot product of one array with itself transposed to get crazier graphs. And you could just do all kinds of fun stuff.
So is any NumPy operation on a matrix supported by dask?
I was going to get to that a little later, but no. Is the short answer. But we do support a lot of stuff. So yeah, but we do have like access arguments too. Anyway, these are just kind of fun to make. And this is like beyond what I can explain from looking at it, but that's the graph that dask makes. So anyway, back to my talk. So that's how we make. Let's start from the beginning. Blah, blah, blah. So collections create graphs like the ones that I just showed you. And I'm going to talk about the collections that we do have next. So I gave a few examples of what dask.array does. It supports most scalar element-wise operations, reductions, slicing, and one thing that's important is you don't always create NumPy arrays from scratch. You often have to load them from external places like some CSV file or HDF5 or something else. And so we support load methods that load from files like this in a blocked way. We also have like tensor products and things like that, but there are some things we don't have. dask.array has limitations due to its nature. This dask.array object keeps track of two-ish things underneath it, which is the shape of the array and the D type of it. So we're not actually computing the array until we call this compute method, where that means we hand the graph off to a scheduler to compute it. So we have to know from the functions that we're using what the output shape of the array is going to be, which means that if your function's output depends on some part of the data that you're passing to it, since we're computing it lazily, we don't know what the output shape is going to be. So things like argware or number of non-zero, things like that, they don't really fit into the way that dask.array is designed. But a lot of other stuff does, and it's still kind of useful. Let's see, up next we have dask data frame, which you can imagine is kind of like a pandas data frame. I don't know. Looks like I have to restart my Python notebook server. Oh, that's because I did that p-kill IPython thing earlier. That'll do it. Yeah, so I have a demo notebook in here. Cool. So, I'm just going to full screen this. So I'm going to import dask data frame with some alias dd, also progress bar, which we'll see in a second, and then some plotting stuff. So I downloaded a bunch of, who here has seen like the New York Taxi data before? A few people? Yeah, it's a pretty fun data set to play around with. It's like 10 big CSV files. I think it's like 30 gigabytes in total. I just downloaded like 4 or 5 of them. And right now they're 12 gigabytes in CSV format. But CSVs are not a very good format for doing a lot of things, because if I wanted to load a CSV file into a pandas data frame, I would have to serialize everything. I'm not guaranteed like a lot of structure, and I'd have to like infer what the data types are from reading it. So I put the CSVs in a binary format. I'm not going to talk too much about it, but this binary format is called Castra, and it does compression on the fly. And so it compressed it to about 3.9 gigabytes. I guess I'll say something a little bit about Castra. So it doesn't compress the data as much as it can. It just compresses it in a way that makes copying it to disk or in memory faster than it would be with something like memcopy. So it kind of tries to find this like nice spot in how much you can compress things and read them at the same time. So Castra knows about dask because one of our developers made it. But Dask also has a front and Castro method, so I'm gonna take this 4 GB taxi data set. And so I'm gonna just show you guys what it looks like. So I'll put something else in my notebook here. So let's look at a little bit of the data. So you have like pickup date times, medallions, which is like the unique identifier for each taxi. I don't know what the hack license is, but I think sounds cool. Like maybe they're hackers or something.
No, it's the driver's license.
Oh, so I have all their driver's license numbers?
No, you have their taxi identifier.
Oh, I thought that's what the medallion was. Okay.
That's what the medallion
is the car.
And the hack license is the driver of the car.
Oh, okay. Cool.
So you can complain about it.
Okay. So they must share cars, I guess.
They do.
Anyway, thank you. So this is kind of what the data looks like. We have stuff about drop-off longitude and latitude, pickup longitude and latitude, trip distance, time, stuff like that. So I'm going to take this data frame and pull out 2 columns and downsample it, and then, yeah, so I'm gonna do that computation. So that's running. I have some big graph, and the scheduler is computing it right now, and I have to talk for like 15 seconds about it. So now I'm gonna plot it. And so this might look kind of familiar. So you are somewhere in here, I think. That's like Central Park up there. It's my first time in New York, so I don't know anything else really. Other stuff, there's Empire State Building, Statue of Liberty. Yeah, so I'm going to do a few little things to this data set. Here I like compute the distance, the Euclidean distance between the pickup location and the drop-off location. So I take like the XY coordinate or longitude and latitude of the pickup and drop-off, and then find the straight line distance between them. So
shouldn't you have used the Manhattan distance?
I guess I couldn't find conversions for that online. I had to figure out conversions for longitude and latitude because that is different at different places. But yeah, maybe that's what this is. So anyway, that's almost done. That progress bar is kind of nice. So I'm gonna plot that here. So yeah, we just computed over like 4 gigabytes of data this distance, and it took, 40 seconds. Could be faster, I guess. It's fast enough. So yeah, most people only travel a short distance in taxis, like 1 or 2 miles, and you'll notice like this big peak here. Does anyone want to guess what that?
The airport.
Yeah, that's probably what it is. You can see these. That's what that big stuff is. There's also a trip distance column in the thing, which I guess is the driven distance. I'm not going to wait for that one to get done. So there's a little sweet spot of like how you're trying to do like a big data presentation of like how much you can compute on your machine that's short enough for a talk, and this is 40 seconds is kind of pushing it. If I get out of this. Anyway, so dask data frame, you have element-wise, row-wise operations, shuffle operations, ingest CSV files, pandas, NumPy, all that fun stuff. Yeah, you can do indexing stuff. A lot of panda stuff we could do, but there are a few limitations, like the Pandas API. It's very, very large, and wrapping it is something we haven't done all of it. We're very open to community contributions for whatever tiny pandas method you would like. Pandas also isn't as good at releasing the GIL as NumPy is. It's getting a lot better. But so by default, dask data frame uses the threaded scheduler. So the GIL not being released on like computationally intensive things can slow us down a little bit. And then there's just stuff that's hard to do in parallel, like sorting, but it's possible whenever we have the time to get around to doing it. The next thing I'm going to talk about is called dask.bag. It's for applying computations over like collections of generic Python objects. Yeah, so it's like a data structure that is like an unordered list or a set with duplicates. It's like the mathy word would be like a multi-set. So I'm gonna demo that out into. Where's that? I think that's the old one. Yeah, so I downloaded 2 days worth of data from githubarchive.com. It's a pretty cool website. You can just like wget some dates and you get, sorry, I'm drinking champagne. So there's so these are my data files here. This is, if you look at the format, it's like 2015, first month, January, first day, and then by the hour. So we have January 1st and 2nd, all the GitHub data of like all the events that happened on GitHub. The size of it gzipped is 180 megabytes, and uncompressed it's about 1.3 gigabytes. So I'm going to do some imports here, and then should be 48 partitions. So dask.bag is loading from these files, loading these JSON files, and it knows to break them up, or by default it's going to break it up into like blocks per file. So let's look at the first JSON thing in the first file, which would be just like one event. So it's got some interesting fields like actor, which seems to have something to do with who did this event. And it's got an event type. I'm just going to start this one running. So the event type is a push event. So somebody pushed something to github.com on January 1st at 00 seconds. And it was for a project called Dave's Bing Rewards Bot. And I like it because Dave named the project after himself. Dave Bagels. Some people do that. It's funny to me. So yeah, I did here I took my dask bag, which I named B up here, and I plucked out the type events. And so I did a frequency count on the types. And so there's types other than push events, like release events, public events, all these things. And here are the different numbers and stuff. So push events are pretty interesting. You could do stuff like who pushed the most. Like that's a fun question to ask for this data set, right? So with dask.bag, we can do something like that. So first thing we would do would be to like filter out all of the things that aren't push events. So we have like a filter function. So I pass in a lambda that gets the type and sees if it's a push event. And if that's true, then it keeps it, and if not, it tosses it. Then if we look at the actor thing, we have some things like their gravatar and their login name. This is David J. So I'm going to pluck out those login names and compute the frequencies. Then from those frequencies, I don't care about the frequencies of every single person who pushed things. I only want like the top K, like top 500 in this case of them. So I'm going to sort that frequency list, and by default it doesn't know how to sort a tuple that's a string and then a number. So I have this kind of a function that tells it to sort by the count, which is these counts up here that frequency has. Yeah, so I should have probably been running that already because it'll take a second. Anyone have a question?
Sure. You're talking a lot about input. What about the outputs? What variables do you have outputs?
So this is outputting a list of tuples. Is that what you're asking?
Yeah, I was just wondering what they were. You showed a PDF. I was wondering what other types there were.
Oh, of visualization outputs?
Anything.
Okay, so the visualization output is more just for like visualizing the graph. It's not necessarily for like I could write this dask bag to files and everything cool. Oh, sorry, he asked about the outputs. I'm supposed to repeat your question. Yes, so you can write a dask bag to a file. There's a lot with dask bag. It can work for a lot of different kinds of Python objects. So it doesn't have as much structured output as like a dask or as stuff you would want from an array or a data frame. So you got to figure out what you want to get it to output. Anyway, so this got done pushing. So on January 1st and 2nd of this year, somebody pushed to GitHub 4,601 times. So let's see who that guy is. His name was Tim.
It's very intense.
Yeah. So I don't know. Looking at this, I buy that he pushed to GitHub 4,000. Like he looks like Jesus. And he's an evangelist. He's all about APIs, evangelizing APIs. And if we look here, he did push to GitHub. Well, wait, that was the day before, so he pushed a lot.
Wow.
Yeah, so that seems kind of inhuman, but he did it somehow. Thank you, Ken. Does anybody know Ken? Hope not. Yeah, I'm pretty sure that was a bot or something that he was doing that. So yeah, there's a bunch of other people in here. Anyone from the room in our list who was writing code on New Year's? Anyway, so back to dask bag. Yeah, so I kind of wanted to show you guys some of the functions that are available with it. Filter, fold, distinct, group by. So dask bag is using our multiprocessing scheduler, and that's one of its limitations. Since it's working on Python objects, we know it's probably going to be doing stuff that isn't going to release the GIL, so we spin up a bunch of processes, but that's also can be a bad thing because we have to serialize a bunch of stuff between processes. So we don't want to do things with dask bag that have a lot of inter-process communication. Also, serializing things between functions can fail. Like pickle can't pickle everything. Dill tries to, but it still screws up sometimes. Things like group by are pretty slow. Fold bys are like reductions with group by, so they go faster because you kind of reduce as you do group by, so it transports less data. And then there's dask imperative. So dask imperative is a little bit different from the other collections because it's not necessarily a data container like the other ones are. Dask imperative is more for annotating code that you already have to build a dask graph. So if you have some custom workflow that doesn't really fit into NumPy arrays or data frames or dask bags, you can use dask imperative. So it has two objects, do and value. Do is like a decorator that you wrap functions with to make them lazy, and it makes a graph out of them. And value is a thing like that. not for functions, but for like objects, but you want to have like method access and attribute access. But you want to make it lazy. So I made the decision to put another fun GIF in my presentation. It was kind of controversial. I don't care if anyone can like understand the code. That's not what this is for. It's just to show like, you know, you don't have to change your code too much to make it work with dask imperative. This changed like 3 or 4 lines. So you have this like main algorithm, and then you're parallelizing it. It's like reading from an HDF5 file and computing it. So yeah, and I thought the GIFs were cool. So dask imperative has limitations, and a lot of the times its limitations are that it can't, your code isn't easily parallelizable, like your functions aren't pure, and you create classes and objects for everything and you shouldn't, or you have a lot of shared resources, your functions aren't, I don't think I've ever said this word out loud before, idempotent, to make them that way, and that's a good thing. Yeah, so it's not, you can't just go around parallelizing everything, and it doesn't make everything always better. A dask imperative value can't be like iterated over since it's lazy, and you can't use it as like a predicate in Python and say like my dask imperative value, if my dask imperative value, then do this, because it doesn't have like a truthiness value to it. And you also can't change them in place. So now I'm going to talk about our schedulers, and here we have a pretty cool GIF. It's so the things that are blue are things that have been called already, and the things that are red are things that are about to be called. So there are several different strategies you could take whenever you are going to like execute one of these graphs. And so the one that we take is, we take like a last in, first out stack, and this helps us minimize memory a little bit too. So like as tasks become available, then we execute the ones that most recently became available. And so this makes it kind of happen like the depth first search. So if you see here, like this circle got done, and then that made this one immediately available above it, so that one executed right after it, and so it kind of traversed up these branches. There's a few fail cases where this will end up like filling like where you will compute a lot of data unnecessarily because you're trying to fill all the dependencies for something that you computed up to first. But for the most general cases, it works pretty well, and yeah, but currently all our schedulers are just basically like, we want to do this in a multiprocessing way or a threaded way. They are not about like graph traversal strategies. In the future, whenever we have like more specific workflows that we want to use dask for, we can modify our schedulers to do special things, but we don't do that yet. So here are 4 schedulers. I think I already mentioned these. Yeah, shared memory ones. And so there is a distributed memory scheduler. It's in beta, and I don't know. I probably shouldn't talk about it because it doesn't work very well. Yeah, it's and I definitely would advocate that like if you have like think you have too much data, you should probably try it on one computer first instead of before going to a cluster. But it's kind of fun to like do things with a cluster. And Continuum has a tool called Anaconda Cluster where you can just like spin up a bunch of AWS instances and compute dask graphs on them. Also, the distributed memory scheduler isn't very, so in a distributed memory environment, you have to have some, you have to think about where your data is at. So one machine might have several workers running on it, and instead of making a network call to get data, it could just like ask the worker that's on the same machine. But dask distributed doesn't really know very much about that kind of thing. So This does work. Yeah, that did not split very well. So this is kind of what the architecture looks like. There's a few clients which have your get method that you give your graph to, and then they pass this graph to the scheduler that distributes piece tasks for your graph out to workers, and then the workers do the computation and the scheduler keeps track of things. Yeah. And so that is the three parts of Dask: the collections, the graphs, and the schedulers. And that wraps it up. I want to thank Continuum and Matthew Rockland and Jim Chris, the other people on the Dask team. And yeah, does anyone have any questions?
So how does this compare to something like PySpark or something like that?
I am not a Spark user, but we are kind of like in this space where we're competing with, where it's kind of, you know, we don't want to compete with Spark because they are a much bigger deal. But yeah, so like if you have Python installed on your computer, you can use Dask. You don't have to do Java stuff. So there's a slower boot up time. But I also don't do very much Spark stuff, so I'm not able to answer that. Any other questions? Here.
Towards the beginning of the you showed the semantics for constructing a graph explicitly. But would it be correct that normally the Dask user doesn't need to deal with that because that is done under the hood?
Right, yeah, so the collections make these graphs, which are just like Python dictionaries like this. So you could go making a custom graph if like one of the collections didn't do what you wanted it to do, and you wanted to like parallelize something, make like a blocked algorithm. But you could also use Dask imperative for that. That's one reason we made Dask imperative, is because writing things like on this slide is not very Pythonic. Yeah, so. You, sir.
Do you have a sparse array as a
The question was, do we have a sparse array? Currently, we do not, but we've been asked that several times, so we've been thinking about implementing it. There's many different like sparse matrix formats, and yeah, we're considering it, and the more people ask that, the more likely we are to make one. So we've been asked that several times. Any other questions?
How about another comparison to PyTables implementation? I know PyTables makes use of NumPy arrays as well.
I don't know very much about PyTables. As far as I know, you can use it to write like a data frame to disk. Is that what PyTables does? Yeah, I think we can load from like that onto the format that PyTable uses. But I think you're interested.
One comment on the PyTable thing. Like, you're absolutely correct. Like your HDF or your H5 example lists out with PyTables.
Okay.
And PyTables is also has like BLOSK inside of it,
Yeah.
like the capture thing you were talking about.
Yeah.
So they share some commonalities, but I've done like PyTables, dask array, .mean, and it's done. It's fantastic. They work
Yeah.
really well together.
So I was supposed to repeat the question on here, but it was like, what about PyTables? And then, yes, PyTables with Dask, good. You, sir?
I was just going to ask if Continuum has this IO Pro tool, and it's also for like large data sets and when you're running into memory problems. And is the approach there similar to what Dask is doing, or is that a completely different thing? Or?
This is another thing that I don't know about, this IO Pro. So, I don't know. Dask is open source, and IO Pro isn't, as far as I know. I think you were next.
So what is the motivation for writing dask? Is it to handle large data sets on one machine? Or is there a possibility to add this distribution over many machines?
Yeah, so that's what dask distributed is for executing like your graphs in a cluster. I think a lot of the motivation is like a lot of workflows don't necessarily need to scale to clusters. Like just because your data is bigger than RAM, it's often better to like apply a blocked algorithm to it on one computer than it is to go to a cluster. Yes.
Another comparison, would it be fair to be comparing this against data core? And like they've got these S-frame and
yeah, I've heard a lot about data core. The question was about comparing dask with data core. I have never used data. So I guess what we need to have there, if you go to dask documentation, and we do have like a comparison thing where we talk about Spark and data, or I don't know if we have a data thing yet, but I think they do have like a parallel out-of-core data frame, which is what we're doing. Our approach is pretty general, so we kind of use the same thing to do NumPy arrays. I don't know if data does that or not. Yes, sir.
Does dask play well yet with other nice continuum I/O products like NumPy? So if you want to, you have a computation and you have too much data to fit it in RAM, but you also need to compute it faster than what you can do in Python or just what NumPy can offer. Can you plug in NumPy somehow?
Yeah, so I think that NumPy, the question was like, does dask play nice with NumPy, which is another open source product that Continuum develops? And I would say it does, but there's not much playing together they do. If you guys say it's playing nice, but because their optimizations are kind of orthogonal. Like NumPy compiles Python to like machine code, so it'll run faster, and dask is more for turning your code into like blocked algorithms and running it in parallel. So
sure. So then can you?
You can use them together.
If you can use NumPy to compile your block algorithm, then you can use dask to run it on the blocks, and it'll be great.
I haven't done that, but I think you could. Yeah.
Okay, that's good.
Yeah. Anything else? Okay. Well, thanks for the questions, everyone.